I'd like to welcome Dr. Mark Fonstad. He's from the University of Oregon. He's an associate professor of geography. He specializes in the physical geography of rivers, the fusion of physical geography with geographic information science, geomorphology, hydrology, and remote sensing. His educational and training includes a BS in geography at the University of Wisconsin. He is a native Wisconsinite, yes. A master's in geography at the Ohio University in Athens, and in 2000, a PhD in geography from Arizona State University. He was a postdoc at Montana State University from 2000-2001. He taught at Texas State University from 2001 to 2011, and he started at the University of Oregon in 2011. So he's going to give us a pretty interesting presentation, kind of talking about, we have so many cool technological tools at our hands, and looking at aerial photography, looking at LiDAR, and what can we use that technology for, and how we understand rivers. So with that, I'm going to let Mark at it.
Good morning, everyone. My name is Mark Fonstad. And, whoa, it's okay. I'll let things get set. There's a lot of slides today because I figured it's the first talk in the morning. People are not entirely coherent, perhaps, so lots of color. But there is one main point. If you're going to take one main point from this entire talk home, it's this, that river science is currently undergoing a methodological revolution. It hasn't quite made it out of the universities yet, but it's starting to. And I'm not entirely sure that the rest of the river community is quite aware of this sort of revolution that's going on, but it will hit you soon enough. So this talk is about this revolution. In order to get to that, however, I'd like to provide some context for photography, which is part of the revolution, and a little bit of its history and use in studying landscapes and in rivers. Right? So might as well start with the Oso landslide from last year. Massive hill slope landslide. It killed all sorts of people. And this was the first thing that people outside that valley saw, was imagery. And the imagery was used to convey what had happened. It was the thing that was shown all over the world. And this imagery was used for the purposes of creating interest. And we sometimes forget that the most powerful use of imagery is actually for propaganda purposes, whether you want to call it that or not. And there is no difference between this and 120 years ago, for example. Here's more imagery of the same area, but from the ground. Now we can flip back 120 years and realize that photography has been used in studying or in commercializing or publicizing rivers and landscapes for a long time. This here is some of the early work by Hiller. I realize I'm the only person in the room who can't see the slides. It's okay. This is from the Powell survey. And its purpose, these photographs' purpose, was to create interest in Congress in order to set aside certain lands for parks and also for people wishing to do development and so on. And this continued all over the place. This is also from the survey. In this case, three-dimensional photography, so that people could actually look through 19th century stereo viewers and get an idea of what landscapes are like that they would never see in their lifetimes. And many of our national parks were set up pretty much on the backbones of photography that were used to promote interest. And we sometimes forget that this is one of the most powerful uses of our data. It's not just for making measurements, but it's actually used for promotional purposes. So here's an example of a photograph, a very powerful photograph. This was taken by Carlton Watkins in the 19th century. And its primary use was to drum up interest in a landscape, in this case Yosemite. And it's also interesting to think about the nature of the photograph. In this case, the photograph was used to point out the permanence of landscape, right? The solidity of the rock. It's always been there. And therefore Yosemite has always been there, and we should use photographs like this in order to make parks, to preserve the landscapes. And these photographs were taken in a certain way to point out that solidity of the rock. And I'll compare this later on with a different way of taking photographs for different purposes. Okay, photography was used ever since for a variety of purposes. Here's a series of photographs taken by the USGS as part of their mission to look at landscape changes over a long period of time. I'm sure you've seen time-lapse picture sets very much like this. In this case, the recession of glaciers. And photography was also used for commercial purposes. This is an example of a stereo pair of an area in Wisconsin. These photographs were taken commercially, and they were sold to people all over the Midwest who wanted to be able to see the world in 3 dimensions. Now, unfortunately, at the time, all it was a visual sort of activity or hobby. People couldn't use these for measurement, but they were used to drum up interest in certain landscapes, and these were very commercially successful. Moving on. So, early days, photography used for commercial purposes, but also for publicity purposes. In the 20th century, we see photography starting to be used for measurement purposes. And the most obvious of this is using aerial photography for measurement purposes, whether they be 2-dimensional or later 3-dimensional measurements. Right? And here's an example of stereo photography from a National Aerial Imaging Program. And this was done by hand, but it was also computerized. And before it was computerized, we actually had these massive, huge, hard copy photogrammetry machines, originally invented just before the World War II. And these machines would allow 3 dimensions to be measured very accurately from stereo photographs. And it's important to point this out because this was the point at which aerial photography became a tool for making direct measurements, not just as an addition, but as a substitute to field measurement. For example, many of the updates of topographic maps starting in the 1950s and 60s were made purely photographically. They weren't made through hand or field surveying. They were made photographically. Things began to change a little bit in the 1970s. And one of the ways that they changed was instead of making photographs or general field descriptions in order to describe rivers or other landscapes, the thought became experiment has been useful for our sciences. And part of experiment has been to measure things precisely. And in order to make precision measurements in the field, it's important for us to have tools that allow such precision. And a whole series of tools began to be invested in river and landscape sciences. For example, we begin to see advanced surveying equipment. I say advanced surveying. You remember this is the 1970s, so not exactly. But this is electronic distance measurements and so on. And it promoted a particular way of measuring landscapes. In this way, in this case, what you're measuring is not that many points, but we're measuring them with high precision. And that high precision was thought to be, and to some degree still is, one of the main important things. In other words, we can have trust in these measurements because they are high precision. At the same time, something was left out. In order to make these high precision measurements, it was believed that we could abstract the landscape down to a smaller number of points or a smaller area where we make direct measurements in order to have that precision. Right. In the early 20th century, measurements were not nearly as precise. There would have been sketch maps or much more generalized maps, but you would have had entire areas. Starting at this point, precision became more important, and we have less of that continuous coverage and this higher precision type of measurement. Right. So we can zoom ahead to the 1990s. And even in the 1990s, not that much has changed. I'm ashamed to say this is me in the 1990s. And I'm holding basically a ruler, right? And this is how we made measurements of rivers, right? Point precision. And that point precision was used to do things like cross-sections or outlines of particular features. And we might use those for various purposes. We might use them to measure geomorphic change or to make cross-sections for flood hydrology, whatever that might be. This case, we have something in the neighborhood of maybe measuring a few hundreds of points or a few thousands of points a day, no more. High precision, but the abstraction of landscape to these points is important in the way we see landscapes. So we go to individual places and make high precision measurements at a few individual places with the idea that in between those points are not are changes in the riverscape that are not that great. That's our assumption. We have to make that assumption because we don't have points in between. We've only got points here and here, and those are high precision points, and we are assuming that the riverscape, whatever features we are interested in, changes gradually from one place to another. This is a set of assumptions built into these measurements. We might try to generalize a little bit. We might take aerial photography, for example, and abstract between measurement areas. Or we might try to use statistics or other analytical tools to compare one set of points to another. But it is necessary to recognize that the way that we measure the landscape has an effect on how we see the entire connected landscape, in this case a network. We can't really get anything between, so we assume that there is gradual change between one area and another. And many of our measurement tools are still like that, right? We go and make high precision measurements, and in this case, where you're underwater, it's quite difficult actually to make measurements more than just at this point or at this point. However, if you're out there long enough, one of the things that's obvious is you know you're missing things that are important. For example, if you happen to be interested in microhabitat, because you think macroinvertebrates are important to the river ecosystem, or for whatever purpose that might be, particle size measurements, you recognize that these points are missing things at certain scales that might be important. And maybe there are ways to measure those things, even though we don't necessarily have the tools currently to do so. Okay, I'm going to skip a couple here. Now, at the same time that I was showing you the picture of me with the ruler, we have a whole number of technologies that have been instituted to try to fix the problem of having high precision in only some areas and large amounts of abstraction in between those areas. The most obvious of these is aerial LiDAR. This is laser scanning for elevation, and we can use that to look at very large riverscapes or other landscapes over a large area. Now, LiDAR is both wonderful and terrible. The wonderfulness of it is that the amount of data that exists is tremendous, and we have complete coverage in many areas. It allows us for high precision change measurement, and it's a very high data quality. That's the good part, right? The tragedy of it is it takes out of our hands the data collection method, which might sound like not such a big deal, right? I don't have to go and collect that data, but it means we are not in control of our own data. We can't get it on that exact day that we want it. We can't necessarily have the money to fly LiDAR every single day for a whole year, or whatever it might be. This has been to remove control over data from individuals and put it into the hands of people making decisions for groups, whether it be companies or states or whatever the organizations might be. It's a kind of transfer of control of data. And that has pros and cons to it. One of the cons is if I needed to do change detection, then the plane just doesn't happen to be available tomorrow. We also have high resolution versions of these for the field. Like this is terrestrial laser scanning, which is basically ground-based LiDAR. And we can use it for all sorts of things, like how inactive is our riverbank, or how unstable is this area, or the particle sizes on the river bed here. This is wonderful data as well. We're starting to get into kind of an area where having to be able to measure the data in the computer becomes a real problem. Like the amount of data is kind of overwhelming. It's very easy to get enough data that it overwhelms our ability to actually use it, other than just pretty pictures. These systems, by the way, this is not a terrestrial laser scanner. It's a sort of a normal total station. But one of the problems with these systems is often the areas below water are not directly imageable. They are something you just sort of say, well, we're going to get a lot of the areas above water, and then below water, we'll do the best we can, and maybe we'll get some cross sections here or there, and it'll work. It'll be fine. Maybe. Right. So here's an example where we've got a pretty complicated landscape. This is a river in Yellowstone National Park, and we're interested in woody debris transport because they had the big fires in 1988, and they want to see how the habitats are changing. And how do you measure a landscape like this? Well, one possibility is you can make a few points with high precision that you measure the characteristics of this river. We measure a cross-section here or some number of pieces of wood over here. Another possibility is instead of making point measurements, we will aggregate. We'll aggregate this landscape into areas, and they don't have high precision, but they're aggregates, and so we can get some kind of a spatial view of things. That's another possibility. It has the same issues, right? If you aggregate, and this is obviously another mechanism of aggregating stream classes, it's another aggregation, you lose precision by doing this. You gain a certain amount of spatial accuracy, but you lose spatial precision. And we might have many reasons for doing this, right? Many of our flood models, if you're going to do flood modeling, don't require tremendous amount of spatial data. We have one cross-section here and another cross-section here, and the hydraulics that most of us were taught as undergraduates are one-dimensional, and we don't really want all that complexity. We like to make the assumption that between the cross-sections there's not a great deal going on, because that's really complicated, and that takes like math and stuff. Right? So one dimension's okay, maybe. Maybe it's okay. The trouble with this is if the goal is to create data that feeds models like this, you're making decisions about how the river is actually seen. In this case, we're collecting data in order that we can do one-dimensional modeling. Now the problem is, if somebody's going to come into me and say, you've collected data on this river. I'm very interested in studying macroinvertebrates and the food webs on that river. Can you give me your data? Or can I buy or whatever, can I get your data in some way? And the problem is that data was not created with the goal of looking at macroinvertebrates. It's not at the correct scale for the dynamics of the macroinvertebrates. The macroinvertebrates are much more interested in the clustering of particle sizes, not the distribution of cross-sections in the river. Okay, I'm going to skip a bit because we're a little bit behind. You get an idea. These measurements translate into certain kinds of products, flood maps or habitat maps, whatever they might be, based on the data. At the same time, I should quickly point out that the photographs weren't completely being ignored. Those photographs began to be incorporated into the science of geomorphology for change detection. In other words, we can use ground photography for seeing how landscapes change through time, volumes, habitat classes, ground cover, and so on. All right. Here's an example from the beginning of our quote-unquote revolution. It comes from a watershed in Texas, the Nueces River, and this is what it looks like. So there's your one slide of the Nueces River. And one of the things we have available to us are regular old color aerial photography. In this case, it's near infrared, but it doesn't matter so much exactly. And one of the things that we've learned is if these photographs are put together correctly, it's possible to make two-dimensional measurements with them. Fair enough, right? You can measure the widths of things and their aerial extent. But another funny thing that was noticed starting in the late 1990s was that the color information in the water, in this case, is related, in many cases, in clear water rivers, to the water depth. Maybe not exactly, maybe not precisely, but a little bit. And maybe there's a way to extract that information and convert it into something useful to us. So this attempt here has a whole bunch of little dots going down the river, and I'm going to show you an example of what you might do with it. Well, here's something that you could obviously imagine doing. This is the water width in the downstream direction of this river for, I don't know, 40, 50 miles. And you think, okay, fine, it's the water width, no big deal. We could have done that a long time ago, not just since the 1990s. Well, I'd like to point out two things. First of all, the scatter associated with data is far beyond what our theories actually produce, our theories of how spatial rivers structure themselves spatially. If you look at the downstream hydraulic geometry or other organizing principles, they do not include this much spatial scatter. And part of the reason for that is that the measurements used to make those theories were from points far apart from one another. And these were not. These were done every 5 meters, 10 meters, whatever that is. And so that scatter gets blown away. Well, as it turns out, it's possible to extract water depths. And I'm not going to go through the optical processing necessary to do this. But you can think of it this way. The deeper the water is, the darker it looks. And there are ways to convert that darkness of water pixel to water depth. It's possible to do that. And by the way, the water depth looks awfully up and down as well. In fact, even more than the water width. And this amount of spatial complexity is exactly the kind of thing that the local microscale habitat people were interested in that most measurements of the 20th century could not give. Is this? Okay, I'm going to move on some of these. Now, this is not an academic talk, so I don't want to give all sorts of spatial statistics or this kind of thing, but I would like to point out this, that when you collect data at high resolution and with very broad extent, it opens up a whole bunch of possibilities for how those data are used. And one of those possibilities is that you can use from the data themselves, you can extract those places in the riverscape where interesting things are happening without having to know about it ahead of time. This is a strange kind of a graph that basically breaks the river into a series of windows of different sizes. The top of the triangle shows the entire river, and the bottom of the triangle shows the river broken up into very tiny chunks, and in between, it's everywhere in between. And what the colors are showing here, or what the shades of gray are showing, are basically those places where the widths of the rivers are more or less like the downstream hydraulic geometry. Is the river smoothly varying or chopped up into lots of little pieces? And in the places where there are these sort of white colors, what we actually see here is that the regressions, in other words, the hydraulic geometry works very well. And the darker areas, it doesn't work very well. And if you're interested in, every single pixel in this graph is actually a hydraulic geometry R squared. So probably this one graph is more hydraulic geometry regressions than have ever been done in human history. But more importantly, it's something that was done in like a minute. This is what you can do when you have broad scale data and you just want to know how to analyze it. And one of the interesting things is the river is in chunks. It looks like the river comes in little chunks. And there are theories for why rivers might do this. I'm going to jump ahead to one here. It may be because when sediment goes into rivers, it's not just coming from some kind of gradual erosion of the landscape or just from tributaries. There are theories such as the sediment links concept that there are point production of sediments, and these point productions of sediments don't just randomly spread the sediment out in places. They come together in links, short bursts of sediments that have particular processes that downstream find them over short distances. And we can see that in broad scale data like this. And this is just aerial photography. This isn't anything new, actually. Okay. Now, a lot of other river theories are also based upon point data, precision data at a few places. For example, in habitats, the river continuum concept, or the hydraulic geometry or some of the theories about energetics in streams. And the problem has always been what happens in between. And the concept of looking at rivers in 2 or 3 or 4 dimensions all at once, which is sometimes called the Riverscape concept, is now something that, well, we never had the data to be able to do it before. And now that we do, people are like, whoa, way too much data. I have no idea how to actually analyze that. So a big price we pay for having too much data is we now have to train people for what to do with the data. This is a big challenge. Okay, here's an example of what you might do. This is a watershed in Scotland. I guess they would call it a catchment, not a watershed. For those of you who are interested in the royalty, this is the same watershed that Balmoral is, where the Queen lives. All right, it looks like this. And it was of interest for salmon habitat, for restoration purposes. And people wanted to know, is the river structured in such a way that certain habitat restorations would work? So you fly a plane over, and one of the things you find out is if you fly the plane low and slow enough and take good quality photography, you can see graininess in the water. And that graininess are actually, well, grains. They're particles. And it's possible to take a textural filter in the computer and pass it over these grains and to actually make estimates of particle sizes under the water, in this case for clear water rivers. So you can make grain size measurements for the entire watershed, which is interesting, useful. Oh, and by the way, if you can also do the water depths and the water widths, and you can do the particle sizes, you can start to generate all those other attributes. The velocities, the shear stresses, the Froude numbers, and so on. This is not a theoretical thing. This is made from measurement. And this is what's been different over the past 10 years, is this ability to generate watershed-wide data measurement-wise rather than theoretical-wise. Okay, and you can take those data and you can use everyday GIS operations to make new kinds of data. This one here has to do with how far would a fish have to swim in order to get to a place where it wants to be, like its spawning habitat. And you notice that you can do this, and it shows that the places in the river, in this particular river, are very small, discrete chunks of the river separated far apart from one another. And if I were in the business of restoring the rivers, that's where I would go. Those are the places I would go. All right. And those places are, like, this is not like some rocket science, right? Like even the bears know that. Right? They know that there are certain places that you go. The trouble is that we are just a few of us, and it would be nice to have techniques that can generate that knowledge for us automatically. Okay, I'm going to skip a bit here. So, by the way, this funny-looking graph shows the relationship between water depth and a ratio between red and green light. And you might think, why are we studying optics in this room? And the reason is red and green are colors we have in normal aerial photography, and their ratio does correlate quite well with depth, which means not only might we be able to get water depths today, but we might be able to get water depths from like 50 or 60 years ago, right? If you have color aerial photography. It's possible we could use this stuff to go back in time. Okay. Well, here's another example of that. On the left is a normal aerial photograph from Texas, and the one on the right is the same photo. It's just been contrasted, stretched to show you what's under the water, and most of that contrast is depth. Okay, and this is an example of doing underwater cross-sections from aerial photos that are about 50 years old. Right? It is possible to do this. And maybe particle sizes, maybe. Okay. Well, I'm not just going to stop with depth. Other things have happened in the last 10 years. For example, we can get people to walk out onto point bars and take pictures with their normal cameras and put them in the computer, and the computer can do photo grain size measurements to high resolution. And actually, the precisions of this are just as good as if you try to do it by hand, except you can do like 1,000 times more. You just take pictures, take more pictures. Sort of interesting thing. And then there was this technique, which was invented by a computer scientist about 5 years ago, named structure from motion. If there was one single technique which has revolutionized the way we measure rivers in the last 5 years, this is it, structure from motion. This is basically how your eye-brain system works. You get 3D information by walking around and seeing things from different vantage points, and your brain can reconstruct that landscape even though we don't have any kind of ground truth measurement. We get a relative sense of who's further away and who's closer by this motion. So this is called structure from motion, and the computer in this case is doing exactly the same thing. You take pictures from multiple vantage points. It's not just stereo imagery. And those multiple vantage points can be used to not only reconstruct roughly where the cameras were in relation to one another, but what the three-dimensional structure of the landscape must have been in order to make those photographs. And this is completely automated. You do basically nothing. Now, of course, if you want to put this in a real space like UTM or latitude, longitude, you have to have a couple ground points, some kind of measurement in order to put them into a space. But you don't need a whole bunch. You just need a few for a point cloud. So let's do an example of this. Oh, by the way, the first person to do this, the computer science student, he published an article called Building Rome in a Day. He took all these pictures from Flickr online and that tourists had taken all over Rome. And just from tourist pictures, he was able to reconstruct the three-dimensional structures of Rome, like the Colosseum and so on, with a few thousand photos, right? So here's an interesting thought. Maybe we can do river measurement by crowdsourcing. Okay, so here's an example of a river. We've got, this is a small river in Texas, and we put a helium balloon with a little kite thing. These things are called heli kites. Take a normal pocket camera and walk down the river, and it's just taking pictures once every 10 seconds. And down below, you'll see a little three-dimensional point cloud. That's sort of like this is a very old one I did about 3 years ago. And this, I don't know, about an hour worth of work, right? So here's another example. This is, again, very old data, and I'm going to show you much better. But this is our very first attempt. You can see us doing this. And all the red points are places where this process produces three-dimensional data. So it's sort of, at this time, it was between aerial LiDAR and terrestrial LiDAR in terms of the point precision and coverage. Here's another example a little bit further on. This is a braided river in Svalbard, Spitsbergen, done from a remote control plane, like the one the kids buy in the airport. And you fly it around for about 40 minutes and come back and land, and the computer can reconstruct where the camera position was. That's what all these little blue squares are. And this landscape underneath is not a LiDAR landscape, so this is completely from photography. So the total cost for this was a day in the field and a $200 little remote control plane. Now you begin to realize why I use the word revolutionary, because it's not capital based, it's based on labor. Okay, so here's an example. This was the very first example I tried. I didn't do this. I didn't take the video. This was somebody else that took a video for their Dorothy Merritt's field area, and they flew a little plane around just to give people an idea for publicity purposes. I took 10 seconds from their little flight. I took it literally off YouTube, and I took the frames of the video and put the frames into the structure from motion software and get 3D data for their field area. Dorothy Merritt came to Oregon about 2 years ago, and when I saw that she was coming, I did this the morning that she came to give a talk, and she was just stunned, because they had been measuring the 3D landscape by hand over a period of a month or two, and I said, oh yeah, that's good. Okay, so if you can do that just from that was a YouTube video, what can I do when I'm really trying to do it? So here's an example where we put the camera, a regular pocket camera, on top of a painter's pole, or that we used to clean windows with or something like that. And you get the little trigger. I think it was actually maybe a slightly better camera. It might have been a DSLR. But in any case, it's got a remote trigger on it, so that you can walk around and just take pictures with the camera on the pole. And this is an area being restored in eastern Oregon. It's an area that's maybe a kilometer long, about a half a mile long, and walk around and take about 1,000 pictures. So this is kind of a one-day kind of data collection process, maybe 2 days. And you should get an idea of the coverage and precision of the data when you recognize that you can see the bark on the woody debris. Not to mention the particle size. Okay, back to fieldwork. I have to remind people, it's not just photography. In order to make measurements, these photographs have to be, the point clouds made from them have to be converted into something, rectified into some kind of space, like UTM. You don't have to have points every picture or something like that. In principle, all you need are a handful of points for the entire point cloud. But it does require you to have some kind of surveying at the end or at the beginning in order to rectify those points. That's for today. 10 years, maybe this will go away, and we'll have GPS in the cameras that are good enough to not need this. I don't know. Probably. So what can you do? Well, this is not just photographs now, right? They're three-dimensional data. We have two kinds of data now in a picture like this. One, we have three-dimensional data that we can make spatial measurements from, like particle sizes, depths, all those other things. The other thing that we have is red, green, and blue color information. And that color information can be converted to do things like classification of habitat, or turbulence, or other kinds of measurements. So these are just examples for doing this. Oh, and by the way, this is now the correct scale that we can use them for habitat modeling and other habitat measurement kind of processes, because the data are coming from a scale that the animals actually see or experience, rather than cross-sections much further apart than they experience. All right. Okay, so these are just two different kinds of organisms, and they're exploring their space. Okay, I'm moving ahead. So here's another example. The first part of this video, whoa. The first part of this video is a landscape shot in this river restoration area from a balloon over a period of about 2 hours. If it looks a little wonky with the red and green, I was supposed to bring 3D glasses for everybody. They're sitting on my desk in Oregon. I apologize, but it looks great to me. So this is not terrestrial laser scanning or aerial LiDAR like this. Is just a pocket camera. I would say the spatial resolution here is something on the order of about 2 centimeters, roughly speaking. It depends exactly where you are. It was not set up in order to do vegetation mapping, but it could be done at least to some degree for this as well. Now, this video has another section to it, which we'll get to in a second here. But I want to point out that in this section, the water is slightly clear enough that we can actually do the water depth mapping from photogrammetry, from the refraction, or from the parallax of light, rather than using some kind of funny color way. So this is a much more precise way of doing water depth as well. And of course, we get the 3D above the land, so full 3D landscapes. Now, this next video is the same kind of a thing, but we put the camera on a helicopter. The helicopter costs money, maybe $2,000 or $3,000 to fly for about 4 hours. But we also flew like 40 kilometers with it. And this one is just showing maybe 10 or 20 miles with it. Whoa, funky color. Is this as good as aerial LiDAR? Yes, it's as good as aerial LiDAR. There are some systematic distortions. We're learning how to fly the helicopter correctly to get rid of those. The question is not, is it better than aerial LiDAR? The question is it better than terrestrial laser scanning? And in some cases, it almost is. Right? And it costs basically nothing. So this is just an example of where things are going, right? Instead of high capital, low capital, and a little bit more labor. So if you're a watershed group wanting three-dimensional measurements, whether for promotional purposes or measurement purposes, it is possible for you to have as good as or better data than anyone ever had if you're willing to put forth labor. You don't just have to have fancy instruments. And you can get data that's watershed quality at high resolution. I'm running out of time. I'm going to jump ahead just a little bit. By the way, these data can be used for stuff more than just the hard stuff in the river. It can also be used for water surfaces. And it reminds me to show you, come back to the Yosemite picture, right? The one on the left is what we've been talking about, the fixedness of landscape, right? But Ansel Adams became famous because he took pictures of stuff that changed all the time. And if we want to know about the water rather than just the bed of the river, it's possible to measure that also. Right? So I have to put in a video from The Matrix. Like you saw 3D in The Matrix because they shot with cameras taking pictures all at once from different angles. And wouldn't it be interesting if we could look at the things moving in the river in 3D at the same time? Well, we can do this now. Skip ahead. I'm going to skip this one. So we can take pocket cameras and wire them together now. It's easy to do. And we can have these cameras shoot all at once. Okay, so it's shoot, and I'm going to skip ahead. So we take pictures of the river all at once. And when they take the pictures all at once, it means we can take something that's moving and actually produce three-dimensional data from it. So here's an example of looking at the water surface in 3D, which you never could do before without photography, because by touching the water, it would change it, right? But if we do it optically, it's possible to do. Now, why would you want to do this? Well, as it turns out, the water surface reflects many of the hydraulic conditions used by macroorganisms, biotopes, for example. And this is one of the ways that it can be measured. And I'm not even thinking about things like sediment transport and woody debris transport and all the other things. So it is possible to do things like use the motion in order to generate velocity maps. Okay. I'm going to finish up with just two things. First of all, there's been a revolution going on. That revolution is not towards high expense, high precision instruments, but rather low expense, medium precision instruments that everybody has. That revolution is changing the amount of data so that our science has gone from being a data poor science to a data rich science, a qualitative difference, making us a lot more like astronomy than, say, ecology. Way too much data. And we have to figure out ways to use that data to our advantage. And secondly, if we're going to be able to use these data, we have to find ways of dispersing it. And the amount of data is tremendous, and so it's not easy, but we have an advantage that we didn't have 10 years ago. Online, there are Flickr and all sorts of other spaces where we can post our pictures, and anybody else can use those pictures. And we are seeing the production in the past 2 or 3 years of an open source revolution in river sciences, where people are sharing pictures and then they can make the 3D landscapes from them. Okay, I'm going to jump to one last slide here. Forgive me. I just put too many pictures in. So here's the last video of the day. This is actually a GoPro, one of those little GoPro cameras, you know, that those crazy people, skiers and whatever, are trying to kill themselves with these GoPro cameras. But this one is actually hanging off the bottom of my canoe. And the paddle downstream. And this is just a little clip, and the GoPro is underwater. And it's possible now to take the frames of these GoPros and extract from them underwater things, without the planes, without the helicopters, without any of that stuff. And I think a little bit more development of this, we're going to see the sort of situation where a group is going to paddle down the such and such river tomorrow. You give them a camera, and they come back, and after a day of processing, you have the bathymetry and particle sizes for the entire river. That's, I think, the direction we're going, the crowdsourcing of river science. Thank you very much. I know it's in the morning, but you know.
Yeah, no. And there's a coffee break after this, so everybody look at the coffee break. Yeah, go for it.
So how do we
you deal with slightly more turbid streams?
Yeah, I figured somebody, I find it slightly hilarious that the place I was asked to give this talk to today is, coming from Wisconsin, is the one place where a lot of these techniques won't work as easily. And the reason for this is that turbid waters, as you would, obscure the optical signal. And so you won't be able to use them for below water bathymetry, this particular technique, structure for motion anyway. Of course, it'll still work great for above water. Right? That works fine. I think, I do a lot of other kinds of remote sensing of rivers as well, radar work on a satellite, sonar work, and so on. I think the single biggest challenge for remote sensing of riverscapes is small turbid rivers, or small turbid streams. And we do not have a technique currently that can handle those in 3 dimensions very well right now. But maybe there's somebody sitting in the room that'll figure out how to put fish finders together to do interferometry or something.
Yeah, Mark, what do you, how are you processing the data? Are you using like ERDOS Imagine or what kind of software?
Yeah, so I think you're probably talking about structure from motion now. The color remote, spectral remote sensing did use a normal remote sensing package like ERDOS. The structure from motion, however, is different. I actually use a high-end package which is called PhotoScan. It's made by a company called Agisoft. And it costs for academics like $500, but I think for professionals it's like $3,000. Now, I call it professional because there are actually free open source programs that'll make point clouds for you doing this process, absolutely free. I bought the Cadillac version of things because it'll also do orthophotograph production, DEM production, and a number of other things beyond just make points. So depending on what you want, you can use software that goes everywhere from free up to, you know, a few $1,000s and everywhere in between.
What have your experiences been with heavy floodplain vegetation?
Right, so one of the biggest differences between doing 3-dimensional measurements via LiDAR and 3-dimensional measurements using photography is how they interact with vegetation. What you can see is what you get in structure from motion. If you have dense vegetation and you put the camera above that vegetation, you will not be able to see what's underneath. Whereas LiDAR can sometimes go through some of that vegetation. So many of the examples I showed today were actually under forest cover, and I was walking around with a camera on a pole because it was the only way that we knew to get 3D, was to do it that way. If you have heavy vegetation and you just feel like you must have aerial mapping, you're going to have to use LiDAR to do that because what you see is what you get from photography.
Other questions? Thankfully, Mark is going to be hanging around with us for the duration of the conference. It's usually Wednesday morning, I believe. So please take advantage of being here. And
I thought you were going to say, please take advantage of him.
definitely do that. Please take advantage of being here to talk about these sort of techniques.
Thank you very much.
Yeah. So we have coffee break. We are going to start promptly at 9:45 because we are a conference that runs on time, right? Right. Exactly. Please also take an opportunity to start visiting our sponsors.